This video is on the periodic table exam questions.
Okay, so we're going to look at question 1 here. So state one similarity between hydrogen and the elements in group 1. Now what we know about groups, they all have similar reactivity, and that's because they have the same number of electrons in their outer shell. Group 1 has 1 electron in the outer shell, group 2 has 2, group 3 has 3, and so forth. So one similarity is that they all only have 1 electron in their outer shell. And now one difference between hydrogen and the elements in group 1. Here we could talk about a number of different things. One thing could be the fact that hydrogen is in period 1 and therefore only has 1 shell, whereas the others are further down the periodic table, more periods and more shells. The other thing you could talk about is actually the fact that hydrogen is a gas at room temperature, whereas lithium and sodium are both solid metals at room temperature. Equally, the fact that lithium and sodium are metals, whereas hydrogen is a non-metal, you could also talk about that. I'm going to stick with the one that links most to the periodic table rather than the types. So hydrogen only has 1 shell. The other group 1 elements have more than 1 shell of electrons. Okay, so now we're moving on to talk about Dmitri Mendeleev's periodic table. So he was one of the first chemists to classify the elements by arranging them in order of their atomic weights. Today we order it by atomic number rather than atomic mass. His periodic table was published in 1869. How did Mendeleev know that there must be undiscovered elements, and how did he take this into account when he designed his periodic table? So when he was designing this periodic table, he was much more interested in the properties of the elements. So if he just placed all the ones that he knew, then there would be elements in the wrong group because they don't have properties that fit that group. And so what he did was he left gaps for them to later be filled when those elements were discovered that fitted the pattern of that group. So 2 marks, 2 points. So how he knew, so consecutive elements would be in wrong group as their properties did not match. And second point, that he left gaps in the table for undiscovered elements to be filled in later. By the early 20th century, protons and electrons had been discovered to describe how the numbers of protons and electrons in atoms allow chemists to place elements in their correct order in their correct group. So we today, as I said, arrange our elements by atomic number, which is the same as the number of protons. And for atoms, in order to keep them neutral, they will have a same number of electrons and the same number of protons. So electrons arranged in order of their atomic number, number of protons, and elements in the same group as we saw in question 1 have the same number of electrons in their outer shell. And then you could also talk about the fact that the number of electrons in outer shell is what determines the chemical properties. And so will be in the correct group. Okay, so suggest why one of the groups that is on today's periodic table was not in Mendeleev's periodic system. So this group is our group 8, and they did not appear on Mendeleev's periodic table because they were so unreactive that they did not form compounds, and so they hadn't been discovered. They were all gases, so it's quite hard to discover those. They're so unreactive that they don't form compounds. So one of the groups that, just so we remember, is group 8, are noble gases, so called because they are inert, which means that they are unreactive. Explain the arrangement of the first 20 elements in today's periodic table. You should explain your answer. You should answer in terms of atomic structure. So they are ordered by atomic number and elements in the same group have the same number of electrons in their outer shell. Give the order of the reactivity of the halogens from the results in the table above. Explain how you use the results to show this order of reactivity. So we've talked about halogen displacement reactions, which is our table of results here. So in our displacement reactions, our least reactive is displaced. So just jot that aside so we remember. Displacement reaction, least reactive is displaced, and that means it's displaced from the compound, so we would then see it as its elemental form. So our chlorine, obviously when it reacts with itself, isn't going to change anything because they're the same reactivity. However, when we react it with potassium bromide, we end up with an orange colour forming, and that's because we've displaced the bromine from that solution. So we then form potassium chloride and bromine, and it's the bromine that causes that colour to be seen. Similarly, potassium iodide, chlorine is displacing that iodine to then form potassium chloride, and we're seeing a colour because of the iodine that's been displaced. So our order is chlorine is more reactive than bromine, which is more reactive than iodine. And we can see that in the table, chlorine displaces bromine and iodine, whereas our bromine, obviously less reactive than chlorine, which we've established here. Same reaction as itself in potassium bromide, but here again we see that iodine being displaced, so we know that bromine is more reactive than iodine. Okay, so we now want to look at why that reactivity order, which I've just jotted at the top here. So chlorine is more reactive than bromine, is more reactive than iodine. So going down the group, we become more reactive. And if we remember back to earlier questions, we said that chemical properties were due to our outer electrons. And so it's going to be dependent on how available our outer electrons are for our reaction. So as we go down the group, the outer electrons are further from the nucleus, and this means that there's a weaker attraction to those outer electrons. And if we remember group 7, when it reacts, it forms -1 ions, and to do that it must gain an electron. And so if we're talking about gaining an electron, we're talking about adding that electron to the outer shell of chlorine. And so if that attraction is weaker going down the group, then it's going to become harder to add that additional electron. Due to the weaker attractive force. Outer electrons are further from the nucleus, and so there is a weaker attraction. Okay, so we're now looking at Newland's version of the periodic table, and we're looking for 3 differences between the groups in Newland's periodic table and the groups in our modern periodic table. So the first one that jumps out to me is that hydrogen is in the same group as the halogens. Also the fact that the halogens are the first group. We could talk about the noble gases not being there. We could also talk about the fact that hydrogen is in the same row as lots of these period 2 elements, rather than them being split up. We don't have this separation between our metals and our non-metals, that metals are in between some non-metals. There's no splitting of those. We've talked a bit about the groups not lining up, so carbon, we know it to be in group 4, but here it's in group 5. So I'm going to go for the fact that actually we only have 7 groups. Suggest one reason why this part of Newland's table was different from the modern one. So we didn't know about the noble gases. And so we couldn't have had that 8th group, as they hadn't been discovered. We didn't know about our protons or our electrons in order to make sure that they're in the same group. See, our hydrogen and fluorine and chlorine, they wouldn't be in the same group because they don't have the same number of electrons in their outer shell. Okay, so we're now looking at Mendeleev's table and what is wrong with tellurium, which is Te, and iodine in terms of their relative atomic masses. So remember, our mass number is our larger number, as it's the number of protons and neutrons, whereas our atomic number is just our number of protons, so our mass number is always the larger one. So tellurium has 128, whereas iodine has 127. Now, he had arranged the elements according to their properties and their relative masses. But if he was ordering them in terms of their relative masses, you would sequentially put 127 before 128. And so that's what this question is talking about, is that they are in reverse order. As tellurium has a larger relative atomic mass than iodine. Explain why this is not a problem in our periodic table. In our modern periodic table, we order the elements by atomic number. And so tellurium is correctly placed before iodine. We also make sure that it's based on electron structure. So they are in the correct group. Okay, looking at question 5, we are explaining by reference to electronic structures why both sodium and potassium are in group 1. So this is coming back to something we looked at in question 1, and that's that sodium and potassium both have 1 electron in their outer shell. Use the datasheet, so the periodic table, to help you answer this question. The diagrams below represent the electronic structures of some atoms and ions. Which one of the structures, A to F, represents a sodium atom? So sodium, we can see on our periodic table, has an atomic number 11 and a relative atomic mass of 23. As they've just given our electronic structure for an atom, we know that this is equal to our protons. For an atom, it's equal to electrons as well. So here we should be looking for a structure that has 11 electrons. So they go 2, 8, which is 10 plus 1 is 11. So C has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons, and so must be sodium. For a potassium ion, now potassium has an atomic number of 19, so for its atom it would have 19 electrons, but for a potassium plus ion, to become positive it must have lost the negative, so it must have lost 1 electron. It's going to have 18 electrons, and so there we're going to be looking for the 288 configuration, so it should have the configuration of a noble gas. So looking at E's jumping out, so 288. Sodium and potassium both react with cold water, so this was one of the demonstrations I did at the back of the class. So sodium plus water goes to sodium hydroxide plus hydrogen. Complete and balance the symbol equation for this reaction. So symbol for sodium we can get from our periodic table, which is Na. Water we hopefully know to be H2O. And hydrogen, we know the symbol is H, but here we just need to remember that hydrogen exists as a diatomic molecule. Which means that we have 2 hydrogen atoms bonded together in a molecule. Now we need to balance it. So checking our number of sodiums, left hand side we have 1, right hand side we have 2. So we need to change our number of sodiums. Our hydrogens we have 2 on the left hand side and 1, 2, 3, 4 on the right hand side. And our oxygens we have 1 on the left hand side and 2 on the right hand side. So we're needing to change all of these as we need them all to be the same for our conservation of mass. So in order to get 2 sodiums, we can simply add a 2 in front of the sodium. Remember, we can only change the big numbers, not the small numbers, as changing the small numbers changes what the compound is, it changes what the substance is. So we only change the large number, how many molecules of that substance we have. Hydrogens, in order to get more hydrogens, again we're going to add a 2. So now we get 4 hydrogens, but this also changes our number of oxygens, as the big number means you do that of everything behind it, whereas our little 2, that only affects the hydrogen, so it only affects what's directly before it. So if it was for more than one element, it would have brackets around it. So here, 2 lots of that oxygen, and now they are all fine, and so it's nicely balanced. So we're now going to look at how the reactivity of potassium with water differs to that from sodium with water. So what we should have seen in this demonstration was that potassium reacts more vigorously or faster and explain this difference in reactivity by referencing the electronic structures of the potassium and sodium atoms. So this is similar to the question we had about the halogens, but for our group 1 we form +1 ions, and so to do that we have to lose an electron. And so as we go down the group we still have that same pattern we had with the halogens. Going down the group, our outer shell electrons are further away, and so we have that weaker attraction, but that means that that outer electron is easier to lose. So potassium is larger than sodium, therefore its outer shell of electron, is further from the nucleus. There is a weaker attraction to the outer electron, and so it is easier to lose the outer electron. So finally now, question 6. The halogens are in group 7. Why, in terms of electrons, are the halogens in group 7? They all have 7 electrons in their outer shell. And then here, in terms of electrons, why chlorine is more reactive than bromine. So chlorine is smaller, and therefore its outer shell of electrons is closer to the nucleus, stronger attraction between nucleus and outer electrons, and so chlorine is able to gain an extra electron easier. And that's all on our periodic table exam questions. Thank you.